In today's video, we are going to be talking about gravitational potential energy. As we said in our previous video, there are two main types of energy: kinetic energy, which is the energy of motion, and potential energy. As we also said in the previous video, energy within a system is always conserved unless it acts upon or is acted upon by another system and changes in energy due to work. Another way to say this is that the energy of an isolated system is always conserved. At the bottom here, we'll have an important tool for solving problems with energy, which is that our total energy of a system is equal to the kinetic energy of the system plus the potential energy of the system at any given time. Potential energy is energy that has the potential to become kinetic energy. This is very important, which is why I wrote it in all caps. A single object cannot have potential energy, no matter what kind of potential energy. Potential energy arises from the interactions between multiple objects, so only a system of multiple objects can have potential energy. As I mentioned earlier, there are many different types of potential energy: gravitational potential energy, and I will be using this notation very frequently, PEG, elastic potential energy or spring potential energy, and I will also be using the PEL right here, and internal potential energy, which encompasses basically everything else for the most part. Today we are going to be dealing mainly with gravitational potential energy. Gravitational potential energy results from the force of gravity acting on two objects. As we learned when we were studying gravitation, any two objects that have mass have a force of gravity between them that attracts them toward one another. This is defined in our universal law of gravitation, which is that the force of gravity is equal to the gravitational constant g times the mass of one object times the mass of the other object over the radius between the objects squared. Because we need two objects to have a force of gravity in the first place, it should make sense that we need at least two objects within a system in order to have potential energy of gravity. In most of the situations we are going to be dealing with, one of these two objects is going to be the Earth, because that is the object that we have the biggest gravitational potential energy towards. Though we have a potential energy of gravity towards any object that has a mass, such as a desk or the chair you're sitting on, these potential energy of gravities are so minute that we can basically just ignore them. Our equation for the potential energy of gravity is that potential energy of gravity is equal to the mass of the object that is being attracted toward the larger object times the gravitational field of the larger object times the height from the surface of the larger object at which the smaller object is currently situated. Now let's put this newfound knowledge to use in our first practice problem. Example problem number 1. What is the potential energy of gravity of a 7 kilogram box about to be dropped from 10 meters high? Now, your first instinct may be to write down the equation for potential energy of gravity and just substitute everything in. However, you've just forgotten the most important thing that I have already said in this video, which is that, a single object cannot have potential energy. So, within this problem is impossible. There is no potential energy of gravity for a box because a box is a single object and it's not part of a system. I'm sorry, you might think that's a trick question, but it's honestly a very important concept that people need to understand. Now, for a real one. What is the potential energy gravity of the box Earth system from example problem number 1a? Now that we said that the box and the Earth have gravitational potential energy toward one another, we can actually use the potential energy of gravity equation. So we know that potential energy of gravity is equal to m times g times h, and within this problem our mass is 7 kilograms and our h is 10 meters. And for the purposes of this video, I'm going to say that g is equal to 10 newtons per kilogram, although in reality it's closer to 9.81. So we have 7 kilograms times a gravitational strength of 10 newtons per kilogram times a height of 10 meters, which means that our potential energy of gravity is 700 joules in this box Earth system. Let's try another problem. Example problem number 2. A 5 kilogram object is dropped from a height of 20 meters. What is its velocity when it hits the ground? Although you can solve this problem using kinematics, it's actually a lot more complicated than you would think, and it's a lot easier to solve this just using energy. So why don't we draw out our LOL diagram, and this time, instead of just having kinetic energy, let's add a bar for potential energy. So we're going to define our system as the object and the Earth so that we can have our gravitational potential energy. So in the beginning, we have our kinetic energy is non-existent because we haven't dropped it yet, and our potential energy of gravity is equal to m, which is 5, times g, which again we're going to say is 10, times h, which is 20. So we get that this is equal to, let's see, that's 1,000 joules. So our potential energy of gravity is 1,000 joules. And I know in my other video I color-coded kinetic energy to be green, so I'll go ahead and do that. So, at the very end of this drop, before the object, whatever it is, let's just say it's a ball, is actually touching the ground, there's an instant at which it is starting to touch the ground but hasn't actually decelerated yet. And so we can say that that is when its potential energy of gravity is equal to 0 because its height is equal to 0. And that means that because energy in a system is conserved and no energy has been transferred into this system because no work has been done on it, we know that all of this potential energy of gravity has to be present somewhere in this system once it's dropped. So, because we know none of it is potential energy of gravity anymore, we can say that 1,000 joules of potential energy of gravity have all become kinetic energy. So, now that we know the kinetic energy of the ball when it's about to hit the ground, we can solve our kinetic energy equation to find the velocity of the object. So we know that kinetic energy is equal to 1/2 mv squared. So 1,000 joules is equal to 1/2 times 5 times v squared. If you simplify that, you get that 400 is equal to velocity squared. So 20 meters per second is our final velocity. Let's do one last problem. A 10 kilogram box, this should say lying on the floor, is lifted 2 meters in the air. What is the amount of work done on the box? Because we are analyzing the before and after of a situation like we did in the last problem, let's use another LOL diagram to represent our situation. Our system is going to be the box and the Earth in order to be able to account for that potential energy of gravity. And for right now, we can ignore whatever force is lifting the box because that's not going to factor into our energy. So I'm going to label my axes real quick. And potential energy of gravity. Because we are not analyzing this box while it's moving, we're only analyzing it before it is lifted and after it's lifted, we can say for certain that there is no kinetic energy in either of these two situations. And to help you out, I'll draw a picture real quick. In one, there's a box lying on the floor, 10 kilograms. And in the other, we have the 10 kilogram box that is at a height of 2 meters off the ground. But because right now it's not moving in either of these two situations, it cannot have kinetic energy. However, in this situation, it does not have potential energy of gravity either because it is resting on the floor. There's no height, therefore there's no potential energy of gravity for it to accelerate towards the Earth. So we can say that there is in fact no energy in the box Earth system at this point. However, in this point, we can see that the box is at a height off of the Earth, which means that it must have some kind of potential energy of gravity. So we know that our equation for potential energy of gravity is potential energy of gravity is equal to the mass, which is 10, of the box times the gravitational field, which again we're going to say is 10, times the height of the box off the floor, which is 2 meters. So our potential energy of gravity is going to be 200 joules. And let's write that right here. 200 joules of potential energy of gravity. We can easily see that there is a change in energy from before and after the box is lifted. And as we know already, our work is our change in energy of a system. So we can say that 200 joules of energy was added to this system by whatever lifted the box. And this is our final answer. That's all for today. I hope you got something educational out of it, and I'll see you next time. Thank you.